T over K. And then of course plus you have R rho I times 2 pi R L. Right? Okay, so that's our total cost expression, and now you can see the cost expression is a function of two different unknowns, R and T. Okay? Well, T pipe is known, because pipes typically come in very specific sections, right? And usually the pressure inside the pipe will dictate what thickness pipe we have to use. So let's say thickness of the pipe is known. It's the thickness of the insulation that we don't know. All right? Everybody's good?
Just
Yeah.
to make sure, the first term equals the change in pressure, right?
So this term represents the cost of the pumping. It's the work done. So work done is always the product of the Q times the, delta P times the flow rate. So delta P is 8 mu L Q divided by pi R to the power 4th. You multiply that by Q, you get the work done, right, per time. Power, yeah, you divide by efficiency to actually figure out how much power you have to consume, and you multiply by the cost. Yes?
So is the capitalization factor there the same one as that one?
Yeah, it should be, right? Yeah. Capital factor should be same, because all you're doing is you're distributing money. Now, in some sense, well, actually, yes and no. Why yes and no?
Different eyes or same eyes?
The I should actually be same, but what would be different?
It depreciates.
Time?
Life of the equipment, right? In some sense, because we are assuming in some sense infinite cost, right? So the life could actually be different, and therefore the capitalization factor could actually be different. So yeah, actually in reality they could be different. Okay, but right now let's just assume they both have 10 years lifetime, and we can just take R to be roughly 0.1. Okay, but whatever it is, it's a known number, right? We can easily figure it out. Okay, so now of course we just take a derivative with respect to both unknowns and set it equal to 0, right? Now this may seem like a complex equation, but it turns out, the solution turns out really easy and really beautifully. So that's why I like this problem. And I was actually very proud of myself when I created it. I used to give it as a quiz problem. I figured I'll just do it for you in class. So the nice thing about this problem is, if you think about it, thickness appears in which terms? Only the last two, right? So you can see when you take d cost, dt equals to 0, the first two terms automatically go to 0. So this problem is actually identical to the one variable optimization problem, right? Right? Great. So therefore, you right away see that you have an expression for the optimum thickness. So therefore you know that thickness is basically known. So this becomes rho E delta T divided by R rho I K to the power half times K or minus 1 over H. Right? Oh. Excellent. And that just makes the problem, so that's what I'm saying. So if the problem was kind of, had all the terms everywhere, this would be very difficult to solve. But this is kind of a beautiful, easy solution. So now that we know thickness, all we have to do is now figure out the expression for radius, and how are we going to get that? Sorry?
Take the derivative of...
Just take derivative with respect to radius and set it equal to 0. And this will again be a simple optimization, because you can see this is a linear term, this is a linear term, this is a linear term. So in some sense you can actually add all those up, right? So this will give you take the derivative of the first term, you get minus 4 times rho p 8 mu L Q square. We could probably even cancel out L before that, right? But it's okay, just no big deal. Yeah, actually, you know what? Let's just cancel that. right? Because L will cancel out from the whole equation. So minus and then divide by eta pi r to power pi, right? Okay, plus everything else is linear in R. You take the derivative, R goes away. So basically, you just add those all up. So that is simply R rho n times 2 pi Tp plus rho e times 2 pi L delta T divided by 1 over h plus what? Plus T, but what T? Which T? T over K, where the T has already been obtained, yeah. Sorry? Yeah, we did. Okay, sorry. Okay, so 1 over T, basically, but now it's T star, right? Where T star is this expression for optimum. So we already know that T star. So we can just plug it there, essentially. So T star over K. Right? So rho e 2 pi delta T and then plus R times rho I times 2 pi T star. Right? Yeah.
In that first term, that Q is the flow rate.
Right, yeah.
So isn't it a function of R?
No, because Q is a constraint. Q depends on R, but that's okay. But Q is the, you have to figure out R to keep Q constant. So Q is a known number.
Okay, so we're keeping Q constant.
Right, because that's a constraint imposed on you, right? Because you have to pump certain amount of liquid.
Okay.
Right?
Because I was wondering why we still keep the R in the denominator.
Right, because we know Q. From the PFD, we know flow rate, right? We know Q.
Okay.
All right, great. So now we are in good shape. I do not want to write this messy, the whole expression again. So I'm just going to take this minus sign away. I'm just going to put an equal to here. Right? I hope you will forgive me. And then I'm not even going to write an expression for radius, but you all can see that essentially it's easy enough, right? So radius, you just take r to the 5 there, you just put the whole thing in the denominator, take 1 to the power 1/5. And you have an expression. So you can see you actually get really pretty expressions for both optimum thickness and optimum radius. And that's, as I said, I kind of really like this example. Right? So it's one of those problems which you can actually kind of, two unknowns, real chemical engineering problem, you can actually get a nice little analytical solution. So I was very happy with that. Okay, how much time do we have left?
5 minutes.
5 minutes, okay. Now I'm going to tell you a few problems where you can write down the expressions, and the expressions become so complex, I'm not even going to do it. Okay? But you can try to do it yourself. So we did a problem of CS reactions in batch, right? A goes to B goes to C. And we optimize the residence time, right? You could also ask yourself that you're also going to optimize the temperature. Because in principle, you could run that process at whatever temperature you want, right? And so instead of just optimizing, and I try to do that problem, as I'm saying very quickly, the mathematics got intractable. So I'm not going to do it, but in pretty much any problem, you can actually put temperature dependency and optimize for that unknown and temperature. The reason it becomes so complex is that exponential dependency of rate constant, right? The Arrhenius relationship just makes everything pretty much intractable. Okay, so, all right, that's it. So no class this Friday, right?